Another application of integration is finding the length of curves, or arc length. And so we're working here on page 452, and we're asked to find the length in number 11 here, the length of this curve, which is x equals y cubed over 3 plus 1 over 4y, from y equals 1 to y equals 3. So first of all, don't panic. This is a function of y instead of a function of x. But the formula works the same way. We'll just switch the roles of x and y. Notice that they give us a hint here, which is a big deal. They're telling us that 1 plus dx over dy squared is a perfect square. That's going to help us out, because if it is, we should be able to take the square root of it. So just keep that in mind, that hint is a big deal. Okay, so the first thing I want to do is I want to show you what it is we're actually dealing with by graphing this function. So you can see here I entered the function, and of course y equals 1 and y equals 3, into Desmos. It handles graphing functions of y pretty well. And you can see here that our goal is going to be to compute the length of this part of the curve, which goes from y equals 1, and I've indicated that point here, all the way over here to y equals 3. So we're trying to figure out how long this piece is. If I ripped it off there and straightened it out, how long would it be? And you know we have a technique for doing that, which we'll apply on the next slide. But this is our goal. I just wanted you to see that what we're trying to do is find out how long that piece of curve is. So the way we do this is we use our arc length formula, which takes some form like L equals definite integral from a to b of the square root of 1 plus, in our case, we're going to do dx over dy quantity squared, and then dy. Notice that x and y have just changed roles here. But this is our goal. Our goal is to compute this integral. So to do this, I like to divide my job up into a few parts. First thing I do is I actually write the function down. So ours is x equals y cubed over 3 plus 1 over 4y. And then from there, I start listing the parts that I need. We're going to need the derivative, and we're going to need to square it. So let's figure out dx over dy, which is the derivative of this function. That's going to be, let's see, what, y squared, because we bring the 3 down. And then minus 1 over 4y squared. And once I compute that, just to get myself a little more organized, I'm going to go ahead and square that derivative. So dx over dy squared is, let's see, y to the 4th. Ooh, the y squared's canceled. There's 2 of those, so that's going to be minus 1/2 plus 1 over 16y to the 4th. So this is the derivative squared, and that's going to end up getting plugged into the formula right there, and we'll add 1 to it. So now let's go ahead and write out what L equals. So L equals, and remember we're computing the length from 1 to 3, so I'll go ahead and plug those numbers in. L equals the integral from 1 to 3, square root of 1 plus our squared derivative, which is y to the 4th minus 1/2 plus 1 over 16y to the 4th. And then I got my dy here on the end. Okay, and what the hint is telling us that this thing right here should be a perfect square. And in fact, I noticed something interesting happens. 1 minus 1/2 is just plus 1/2. So when I write this simplified integral out, and I guess I'm just going to try and put it right here before we go to the next screen. This is really going to be from 1 to 3 square root of y to the 4th plus 1/2 plus 1 over 16y to the 4th, and then dy. We'll continue on the next slide, but the idea is that this thing must be a perfect square. We know that because of the hint, but we also can factor this thing and find that out as well. In fact, take a look at what happened here. This was a perfect square, and it had a minus sign, and its factor is y squared minus 1 over 4y squared. And since the only difference is that this one has a plus sign, I got a feeling that our factored form is going to have something to do with or look a lot like y squared minus 1 over 4y squared. Let's get a new screen. So we're working on this definite integral, and we're going to use the fact that we know from the hint that this expression is a perfect square. And so when you factor that, here's what this factored form looks like. It's the same binomial that we had earlier, but it's going to have a plus sign in there. So this is going to be y squared plus 1 over 4y squared squared. That's the factored form of y to the fourth plus 1/2 plus 1 over 16y to the fourth. And you can pause the video right now if you want to go ahead and multiply this out and make sure that I'm right. But I am. Not always, but this time I am. And the reason that's a big deal is we would not be able to perform u substitution on the original radical. But if it's a perfect square underneath the radical, that's called the radicand, we can take the square root, and that radical will go away. So the square root of that thing squared is just y squared plus 1 over 4y squared. And now we can simply do the antiderivative here and use our fundamental theorem to compute this definite integral, because this is just a polynomial. So the antiderivative of y squared is y cubed over 3, and then 1 over 4y squared, that's going to be minus 1 over 4y. You can check the power rule there with a -2 for the exponent if you want to double check it. And don't forget, we're going to compute this from 1 to 3. Okay? So now it's just a matter of plugging these values in. I think what I'll do is to have one last screen here where I'll figure out the value of this definite integral. So let's plug these values in and compute the value of the definite integral. In other words, we're going to find the length of this particular piece of curve. So when I plug in a 3, I get 27 over 3. That's going to be 9 minus 1/12 minus, plug in a 1, I get 1/3 minus 1/4. 1/3 minus 1/4 is also 1/12. So this thing's going to be 9 minus 1/12 minus 1/12. That's 9 minus 2/12 or 1/6. And let's see, that's 54 over 6 minus 1 over 6. That's going to be 53 over 6, which happens to be the correct value. Just short of 9, 8 point something, if you will. I don't like that 6. Let's just fix that a little bit. So the length of the curve is almost 9 units, right? 53 over 6 units. And so this is the strategy that we use. Please remember that little trick with the perfect squares, because usually for the problems that we assign, you're going to end up with a minus 1/2 and a plus 1, which just changes the sign, and you can factor it and take the square root, and then you're okay to use your power rule and the fundamental theorem to plug these numbers in. Don't panic, we're just starting to work with these. We're going to practice more, but this one is a good way to get going here. Good luck, and we'll see you soon.